Physicists have long believed that our universe began with a monumental event called the Big Bang, an explosive expansion that occurred roughly 13.7 billion years ago. This singular moment is considered the starting point of everything: space, time, matter, and energy. According to the prevailing theory, all the contents of the universe were once compressed into an unimaginably small, dense point. Then, in an instant, this point expanded outward in a burst of energy, setting in motion the cosmic evolution that continues to this day. But this leads to a fundamental and still unanswered question. What actually caused the Big Bang? Why did this tremendous event happen in the first place? And what, if anything, came before it? Over the years, scientists have tried to address these profound mysteries through observations, theoretical models, and complex simulations. The Big Bang theory has been the cornerstone of modern cosmology, and it has withstood countless tests. For decades, it has served as the most comprehensive and widely accepted explanation for the origin and structure of the universe. Thousands of scientists have dedicated their careers to studying the formation of stars, galaxies, and cosmic background radiation, each piece of data strengthening the case for the Big Bang. Observational evidence, such as the cosmic microwave, background, and the redshift of galaxies, has consistently supported this model. It offers a coherent narrative of how the universe began as a hot, dense plasma and evolved into the intricate, structured cosmos we observe today. A key element of the Big Bang theory is the concept of dark energy, a mysterious and invisible force thought to be responsible for the accelerated expansion of the universe. Dark energy is believed to be even more abundant than the energy found in galaxies, yet its nature remains elusive. Acting as a kind of anti-gravity, it pushes the universe outward, counteracting the pull of gravity and driving galaxies farther apart. The presence and influence of dark energy have been confirmed through multiple independent observations, and it plays a central role in explaining the current dynamics of the cosmos. However, despite decades of supporting evidence, our understanding of the universe is now being challenged by a new wave of observations, thanks to the revolutionary capabilities of the James Webb Space Telescope. Unlike any telescope before it, the James Webb is able to peer deeper into space and further back in time than ever before. Equipped with advanced infrared technology, it can detect faint light from the earliest galaxies, formed just a few 100 million years after the supposed Big Bang. And what it's revealing is nothing short of astonishing. The James Webb Space Telescope has detected over 750 previously unknown galaxies, far more than scientists had anticipated at this stage of cosmic history. Not only are these galaxies unexpectedly numerous, but they also display characteristics that defy established cosmological predictions. Many of them appear too small, too smooth, too old, and too well organized for their supposed age in the case early universe. These findings are beginning to shake the very foundation of the Big Bang theory. While the average person may be captivated by the beauty of these distant galaxies, to researchers, the concern lies in how poorly these images align with current models. The galaxies captured by Webb are not the chaotic, irregular structures expected of young, cosmic formations. Instead, they exhibit the elegant symmetry and clear organization of spiral galaxies, much like the ones we see today. This is highly problematic for the Big Bang model, which suggests that early galaxies formed through frequent collisions and mergers, gradually building up into larger and more organized systems. The lack of evidence for such mergers among these ancient galaxies raises serious doubts about whether this process occurred as previously believed. In fact, the scientific community's reaction has been dramatic enough that some articles describing the discoveries have even used the word panic in their titles. That's because these galaxies, many of which date back to the earliest stages of the universe, do not conform to the predictions made by decades of cosmological theory. According to the Big Bang model, the early universe should have been a turbulent place, with galaxies in constant motion, colliding and merging in chaotic interactions. Yet the James Webb images show galaxies with smooth, uninterrupted structures, lacking the irregularities we would expect if they had formed through such violent processes. Moreover, these galaxies are significantly smaller than similar ones observed by the Hubble Space Telescope. This runs counter to the expectations of the expanding universe hypothesis, which predicts that distant galaxies should appear larger due to the stretching of space over time. Instead, what we're seeing are compact, mature galaxies that don't seem to match this predicted behavior. The implication is that something fundamental may be wrong with our understanding of how space, time, and matter evolved after the Big Bang. These discoveries also cast doubt on one of the most basic features of the Big Bang theory, the timeline of cosmic evolution. If these ancient galaxies are indeed older than we thought possible for their apparent distance from Earth, then our model of the early universe's development may need serious revision. The James Webb Space Telescope uses sophisticated filters that capture infrared light, light that has traveled billions of years to reach us. By studying this light, astronomers can estimate the age of stars and galaxies based on their color and brightness. The data suggests that many of these galaxies formed earlier and developed faster than our models allow. To better understand the significance of these findings, it's helpful to revisit the original concept of the Big Bang. At the very beginning, the universe was believed to exist as a singularity, a point of infinite density and temperature, where the known laws of physics break down. This singularity marked the origin of space and time. Under the influence of extreme conditions, the universe exploded outward in an event known as cosmic inflation. This period of rapid expansion occurred in less than a fraction of a second, stretching the universe exponentially faster than the speed of light. It is thought that this inflationary phase was responsible for distributing matter evenly throughout the cosmos, creating the seeds for galaxy formation. Following inflation, the universe continued to expand at a slower but steady rate. As it cooled, particles began to form and interact, leading to the creation of atoms and eventually stars and galaxies. During the first few minutes after the Big Bang, a process known as nucleosynthesis occurred, producing the basic elements such as hydrogen and helium. Over billions of years, these building blocks combined under the force of gravity to create the structures we see today: galaxies, stars, and planetary systems. The redshift of light from distant galaxies has long been used as evidence for this expansion. As the universe stretches, so do the wavelengths of light traveling through it, shifting them toward the red end of the spectrum. This has been a foundational observation in cosmology. However, the latest data from the James Webb Telescope introduces complexities that aren't easily explained by redshift alone. The images do not reflect the kind of distorted, merging galaxies expected in a younger universe. Instead, they reveal mature, stable galaxies far earlier than anticipated. Another problem lies in the apparent sizes of these galaxies. If the universe is expanding as we believe, then the further we look, the more stretched out and diffuse these distant galaxies should appear. But instead, we're observing compact galaxies that maintain structure and detail, contradicting the optical effects predicted by an expanding universe. This suggests that either our understanding of expansion is flawed, or these galaxies never followed the developmental path we've theorized. There's also the issue of mergers, or the lack of them. If galaxies formed by combining smaller units over time, as the traditional model claims, then the early universe should be filled with irregular, clumpy systems in the process of assembling. Yet the James Webb images show elegant, disc-shaped galaxies, suggesting that these systems formed in a relatively stable and undisturbed manner. If they didn't grow through mergers, then perhaps they were never small to begin with. This directly challenges a core assumption of galaxy evolution under the Big Bang framework. Even more puzzling is the abundance of galaxies. There are simply too many of them, given the time frame in which they supposedly formed. Their sheer number, along with their structure and maturity, presents a scenario that the Big Bang theory cannot easily explain. This has led some scientists to propose that either the Big Bang needs significant revision or that an entirely new model is required to explain the origin of the universe. In light of these discoveries, the scientific community is entering a period of intense re-examination. The James Webb Space Telescope is not just showing us beautiful images of distant galaxies. It's forcing us to confront the possibility that our understanding of the cosmos may be incomplete or fundamentally flawed. While the Big Bang Theory has guided us for nearly a century, the evidence now emerging from deep space may point toward a deeper, more complex story, one that has yet to be fully written.